I will have another example in which it is going to be a only the it won't be a stick sense itself. Let me start with the example in which this stochastic process is a stick sense stationary process. The given xt is a stick sense stationary process with finite second order moment. So, you do not want the finite second order moment for the stick sense stationary process, but I have taken as example the given xt is going to be a stick sense stationary process along with the finite second order moment. Now, I am going to define the another stochastic process with the random variable y of t, that is a plus b t plus x of t. So, this is going to be a stochastic process. This is a stochastic process y t. Now, we want to check whether the y t is going to be a stationary stick sense stationary process or not. As well as whether this is going to be a wide sense stationary or not. The xt is a stick sense stationary process. Suppose you find out the mean for this random variable, if you find out the mean for the y of t, where a and b are constant, therefore, this is going to be a function of t. Since a and b are constant, the mean of y of t is a function of t, therefore, this is a function of t. Since it is not satisfying the first property of the first condition to become a wide sense stationary process, therefore, the y of t is not a wide sense stationary process. We started with the stick sense stationary process and we created a new stochastic process y of t, that is a plus b t of x t plus x t, where a and b are constant. Now, if you find out the mean of y of t, mean function, that is going to be a function of t, that is nothing but that depends on t. Therefore, y t is not going to be a wide sense stationary process, whereas x t is a stick sense. Now, similarly, you can cross check whether the joint distribution of y of t and shifted by h, t is shifted by h, you can conclude this is also not going to be a, since it is a function of a t, since it is a, the mean is going to be a function of t and the y of t also involves the function of t as well as x of t. Even though x of t is a stick sense stationary process, the way you made a plus b t plus x t, you will end up the joint distributions are going to be different by the t with the shifted t plus h, it won't be satisfied. Therefore, you can conclude y of t is not a stick sense stationary process also. That means, from this example we can conclude whenever you have a stick sense stationary process, if you make a plus b t plus x t, definitely the y of t is not going to be a wide sense stationary process as well as a stick sense stationary process. We will go for the third example. In this third example, let me start with the stochastic process be here this each random variables are uncorrelated random variables with the mean of each random variable is going to be some constant k, which may be assumed to be 0 in some situation. So, in general you keep the mean of each random variable is going to be some constant k, and you make x of m x of n, that is going to be its variance for m is equal to n, and for all other quantity you make it 0. Not only this, each random variables are uncorrelated random variable, that means if you find out the correlation coefficient, that is going to be 0, and the mean is going to be constant, and the expectation of the product of any two random variables, if they are different, it is 0, and obviously if they are same, since you make the assumption, therefore this is going to be a variance sigma square. If you cross check all the properties of all the conditions of the White-Sands stationarity properties, starting with the mean function, and second order moment exists, that is finite, and the covariance function of any two random variables is going to be a function of only the difference, that all those three conditions are going to be satisfied. Therefore, you can come to the conclusion, I am not working out here, this is going to be a weakly stationary process or White-Sands stationary process, or it is going to be called it as a covariance stationary process also. And this stochastic process is also called a white noise process. This is very important in the signal processing. You keep the uncorrelated random variable with this assumption, the mean is going to be a constant, which may be 0, and the product of expectation is going to be these values, and this is going to be a weakly stationary process, in the sense it satisfies all three conditions of that weak sense or White-Sands stationary process, and this stochastic process is called a white noise process. Note that this stochastic process, we did not make the distribution of each random variable xn. What is the distribution of xn is not defined here. Without that, we give all the assumptions of the mean and variance. Therefore, this is going to be very useful in the time series analysis as well as the signal processing, and this particular stochastic process is called the white noise. And sometimes we make the assumption the xn's are going to be normally distributed random variable also, but in general we won't define, we won't give what is the assumption, what is the distribution of xn. Without that, this stochastic process is going to be called it as a white noise process. Addition to the White-Sands stationary process, one can assume that ergodic property also satisfied along with White-Sands stationary property. For illustration purpose, we have discussed Bernoulli process. That means the given stochastic process is a White-Sands stationary process, as well as it is the ergodic properties also satisfied. In that case, the mean function is going to be a sum independent of t, that you can make it as the mu, and the auto covariance function is going to be a R of tau only, because it is a Whiteson stationary process. Therefore, the mean is independent of t, and the autocorrelation function is going to be a function with the only tau, and we have a ergodic property. Therefore, you can find the mean can be estimated from the time average. So, this is possible only if the ergodic property is satisfied. So, the mean can be estimated with the up arrow, that means the estimation of a mean, that is same as 1 divided by 2 times t and minus t to t of x of t dt. So, this is possible as long as the stochastic process is so in general I define t belonging to capital T, that t is different from this t. So, here you have the time interval of the length 2t. Within the 2t, if you find out the time average, and that time average quantity is going to be the estimation for the mean. That means, if mu t converges in the squared mean to mu as a t tends to infinity, then the process is going to be a mean ergodic. That stochastic process is going to be called it as a mean ergodic process. Similarly, one can estimate other higher order moments also, provided the process is ergodic with respect to those moments. So, here I have made the ergodic with respect to the mean. Therefore, you are estimating the mean with the ergodic property. Similarly, if the given stochastic process is satisfying the ergodic property with the higher order moment, then those measures also can be estimated in the same way. So, here the mu t converges in in squared mean to mu as a t tends to infinity. So, that is the conclusion we are getting from the ergodic property along with the Whiteson stationary property. With this, let me stop the today's lecture. Thanks.